Hello and welcome back to your Chem 4 lecture. We are moving on into Chapter 9 this week. And Chapter 9 is all about solutions and concentration. So that's what we're going to talk about. Now, solutions are really important both in chemistry and in the real world. In chemistry, because oftentimes when we are in lab, we have our reagents, our reactants are dissolved in water, because water is a very convenient medium for a lot of different reactions to occur in. Basically, water dissolves a lot of ionic compounds and acids, for example. And when you mix two things that are dissolved together, they freely mix with one another. And so they react very quickly, as we've seen in lab. And then in the real world, of course, solutions are used to, for example, intravenous drips, like what we're looking at here. This is a dialysis setup that we're looking at here. This is basically when your kidneys are having problems regulating the amount of water in your bloodstream, you need some extra help from what's called a dialysis machine to basically remove that water to keep your blood at the right concentration. So the idea is basically based on the concentration of the electrolytes in your blood, you may need to remove water or add water in. So that's what we're going to talk about today. Now, solutions themselves are defined as they're homogeneous mixtures of two or more substances. So remember, a homogeneous mixture means it's in the same phase. So everything is dissolved perfectly together, just like salt water. Now here we see it before it's mixed. So here it's a heterogeneous mixture, but once you mix it together, you would have a homogeneous mixture with the salt dissolved in the water. There's always at least two components to a solution. You have what's called the solvent. That's what's present in the greater amount. And then the solute, which is what dissolves in the solvent. So in this example, we're adding salt to water. Water being the greater amount here is the solvent, and it is dissolving the solute, which is the ionic compound sodium chloride. So solutes include the solids that we talked about, so solid ionic compounds, but it can also include liquids and gases. And solutes will spread evenly throughout a solution. So the solute particles themselves mix with the solvents, and the solute and the solvent then have the same physical state. This is why when we dissolve a solid compound, we call it aqueous. In other words, it's dissolved in water. So it's not liquid in and of itself, but thanks to water, it's dissolved in the water. Now, you cannot separate it by filtration. For example, salt water. If you take water from the ocean, of course, there's particulates that you can filter out, but the salt will still be in there until you evaporate off the water. And yeah, again, these solutes won't be visible, although some of them will give color to a solution. So if you think back to the lab, you did copper-2 sulfate in water, and you noticed that was a blue solution. That's because of the copper-2 ions that were in solution. Yeah, oh, and here's the exact example here, copper-2 sulfate. So if you just take copper-2 sulfate and put water on top of it, well, here you have solid copper-2 sulfate slowly dissolving into the water. You can kind of see there's a gradient here. And after a long enough time, or after you stir it, it dissolves evenly throughout the solution. But you can see the color is given to it by the copper-2 sulfate, not from the water itself. Yeah, okay, so we'll talk briefly about these other types of solutes and solvents here. You can have gas dissolved in a gas, for example, air. Air is a mixture of nitrogen and oxygen for the most part, and it's about 80% nitrogen, 20% oxygen. So you'd say that nitrogen is the solvent and oxygen is the solute. Now, in the case of gases, gas particles don't interact like what we talked about in the last chapter. So they're just kind of bouncing around. They don't really notice each other per se, unless they're involved in a chemical reaction. So that's not the case in air. Okay, there's also liquid type solutions. So there's obvious examples of gas dissolved in a liquid. So for example, if you take a can of soda, you know that there's carbon dioxide bubbles in the soda water itself. So that's a good example of a gas that's dissolved in water. Now, if you were to just take tap water out of your sink, you would also have gas dissolved in there. Air dissolves into the water. It's just that you can't see it. Now, one thing that's kind of interesting, and we'll talk about this in a little bit, is as you heat water up, the solubility of gas particles goes down. So when you're heating up water, you'll actually see bubbles form, even though the water might be at 60 degrees Celsius. So that's not from the boiling, that's actually from the gases that are dissolved in the water coming out of solution. Let's see, what else? You can also have liquid in a liquid. So vinegar, for example, is acetic acid dissolved in water. It's about a 5% acetic acid solution. Yeah, and it's again, the solute there is acetic acid. That's this HC2H3O2, and then the solvent is water. You can, of course, have a solid dissolved in a liquid. That's what we've been talking about with, for example, seawater that has sodium chloride dissolved in water. And just to give an example of a non-water solvent, you could have, for example, ethanol dissolved iodine, I2 here. And tincture of iodine can be used for various sanitary purposes, including cleaning up water. Oh, and then finally, there's also solid solutions. I almost forgot about this, which are basically alloys. For example, brass is an alloy that consists of zinc dissolved in copper. So it's solid, but there's zinc particles mixed into the copper particles. And then steel is carbon dissolved in iron. Yeah, so we've already talked a lot about water being a solvent. The reason for that is basically that it is used as a solvent in nature, and it's also the solvent that's in our body, that all of our biological processes take place during. So that forms a the reason for that is because water is a polar molecule. This is what we talked about a couple chapters ago, where the oxygens are partially negatively charged and the hydrogens are partially positively charged. This allows it to interact with a lot of different biological components. And yeah, they form hydrogen bonds as intermolecular interactions. Okay, so how do solutions form? Well, solutions will form when the interactions between the solute and solvent particles are large enough to overcome the solute-solute interactions and the solvent-solvent interactions. So you can think of it like mixing a group of people at a party, for example. Like if you have two groups of people that all know each other really well, but they don't know people from the other group, they're going to be stuck with each other. That's the solute-solute interactions and the solvent-solvent interactions. But if you get people who know each other relatively well, maybe they're ready to talk to each other at the party, then all of a sudden the interactions from one group to the other overcome the barrier, and so the people are able to interact, and in the same way the solute and the solvent molecules are able to interact. Now, the principal rule, the rule of thumb that we use for whether solutions will form or not, is this idea that like dissolves like. In other words, solutes that have similar intermolecular forces as the solvent will tend to dissolve. Whereas if they are unlike, in other words, if they have different types of intermolecular forces, then they won't dissolve. So for example, if you have a solute that's polar and a solvent that's polar, then a solution will form. If you have a solute that's nonpolar and a solvent that's nonpolar, also that solution will form. However, if your solute is polar and the solvent is nonpolar, then they're not going to interact with one another because they don't have interactive forces bringing them together, intermolecular forces that bring them together. Same thing if you have a nonpolar solute versus a polar solvent. Again, polar solutes will dissolve in polar solvents. Nonpolar solutes will dissolve in nonpolar solvents. So here's an example of solutions that include ionic solvents. So we've already talked about this. It's one of the easiest ones to come up with because we all have experience with it. You know that sodium chloride, table salt, dissolves in water. And what happens is when an ionic compound like sodium chloride that's soluble in water is mixed in the water molecules, you start from this three-dimensional crystal lattice that we talked about so much this semester. And what ends up happening is slowly the negatively charged chloride ions will be peeled off by the partially positive charged hydrogen atoms on water molecules. And so you end up with this arrangement here, where each chloride ion will have 5 or 6 water molecules all kind of hugging it with a positive, partially positively charged hydrogen interacting with the negatively charged chloride, and vice versa for the sodium ions. The sodium ions are slowly peeled off by the partially negative oxygens on the water molecules. So you get this sodium ion that's surrounded by the partially negative oxygens in solution. Okay, so this is what happens with ionic solutes. That's why ionic compounds are able to dissolve in polar solvents like water. Oops. Again, if you have a polar molecule like methanol, that methanol has an OH group in it. An alcohol group is what we call that, which we'll learn about more in a little bit. Because of this OH group, we know that number one, it's a polar molecule because it's got an oxygen-hydrogen bond. That's polar. This oxygen having two lone pairs will be bent in structure, so it's asymmetric, so it's polar. Then, because of this OH bond, we also know that it forms hydrogen bond intermolecular interactions. So because it can have intermolecular force, intermolecular hydrogen bonds, we'll have intermolecular hydrogen bonds with water. So the presence of this alcohol group, we know right away that methanol is going to mix with water. However, if we just had a totally nonpolar molecule, like for example, propane, propane is all carbon-carbon and carbon-hydrogen bonds. As a liquid, propane will not mix with water because it's nonpolar. Okay, let's do a quick check. We want to identify first the solute and solvent in each of these following solutions. So this is just a learning check. This isn't on your sample exercise packet. Just, you know, we're just checking your whether you're paying attention or not now. So just tell me which one is the solute for A, B, C, and D. Go ahead, pause the video here, and when you come back, we'll look at the answers. So for A, if you have 2 grams of sugar in 100 milliliters of water, well, the sugar is obviously less than the water, so sugar is the solute. 60 mils of ethyl alcohol and 30 mils of methyl alcohol. 30 mils is lesser than 60 mils, so the methyl alcohol is the solute. If you have 1.5 grams of sodium chloride in 55 milliliters of water, 1.5 grams, of course, is the lesser. So that's another solute for sodium chloride. And then finally, 200 milliliters of oxygen with 800 milliliters of nitrogen. The oxygen has to be the solute. So there's our answers. Okay, next step. When solid lithium chloride is added to water, it dissolves because, hey, the lithium ions are attracted to, tell me which one. Is it attracted to the oxygen atom or the hydrogen atom of water? And then which one is attracted to the chloride atom? Is it the oxygen atom or the hydrogen atom of water? Go ahead, pause the video, and we'll take a look. Okay, so the lithium ion has a positive charge. That means that's going to attract the partial negative charge of the oxygen atom. And the chloride ions have a negative charge. That's going to attract the partial positive charge of the hydrogen atom. Okay, finally, we're ready for our sample exercise here. Which of the following solutes will dissolve in water and why? Is it A, sodium sulfate, gasoline, B, which is, I'm telling you, nonpolar, and then iodine, and then finally hydrogen chloride, hydrochloric acid. Guess which of these will dissolve in water? And it can be more than one. So go ahead, pause the video, try to think it through, which one's going to be polar and which one's nonpolar. And then when we come back, we will come over the answers. So go ahead, pause the video. Let's take a look. Well, sodium sulfate is ionic, and we know that ionic compounds tend to dissolve in water because water is polar. Gasoline, however, is nonpolar, and you can kind of guess that. You know that if you ever go to a gas station on a rainy day, you'll see like a sheen of oil or gas on top of water. So that tells you that they're not mixing because you can see that sheen. Iodine is nonpolar, right? There's only one iodine-iodine bond in iodine, and that's going to be a nonpolar bond because the electrons are shared equally between the two iodine atoms. So nonpolar means it's not going to dissolve. And then finally, HCl is polar, so it will dissolve, is what we predict. Okay, so electrolytes. So we talk a lot about electrolytes in terms of like, for example, like if you're hydrating, if you're doing exercise, you know that, oh, I got to make sure that I maintain my electrolytes and maintain my hydration. Well, what does that actually mean? Well, electrolytes are ions. That's sodium, potassium chloride, bicarbonate, for example. And these are crucial to maintaining both your blood pH, and also the ability of blood to transmit water and nutrition throughout your body. So we'll talk about electrolytes now. So there's a few different classes of electrolytes. We have first the strong electrolytes. Strong electrolytes are ionic compounds that dissociate 100% in water. And that sounds like a difficult thing, but really all I'm saying is that means that the sodium chloride, for example, dissolves completely to sodium ions and chloride ions. And these solutions will conduct electricity very strongly. So like, for example, if we have a light bulb here with an electrolyte solution in here and kind of this open wire here, if we stick the two wires together, it's as though the wire's connected and the light bulb is going to light up. And so any ionic compound that's soluble in water will be a strong electrolyte. The other thing that is strong acids, which we'll talk about here in a little bit. Now, a weak electrolyte is exactly what it sounds like. It only partially dissociates in water. Now, we haven't really talked too much about this yet because it's more of a complicated topic, but basically, these dissociation reactions have a reverse reaction, which is the recombination reaction. So if you look at, for example, hydrofluoric acid is a weak electrolyte because in water, about 1% of the molecules, HF molecules, will dissociate into hydrogen ions and fluoride ions. So that means that we got like 99% HF molecules, which are not ionic. And the ionic compounds are what is important in terms of conducting the current. So for example, looking at the strong electrolyte here, the reason that a current can be conducted through the strong electrolyte is because you can have net motion of ions. The chloride ions are all attracted to the cathode here. Sodium ions are all attracted to the anode here. And so you have a net movement of current, a net flow of current, in this case, from the anode to the cathode. And that's what completes the circuit for this light bulb. With a weak electrolyte like HF, well, hopefully they're not using HF. HF is super toxic. I'm assuming they're using some other, maybe acetic acid is a good example, if you're going to do it in real life. Same idea, a weak acid gives just a few ions in solution. And so mostly you have these undissociated molecules lying around, and they don't have a charge. They're not positively charged or negatively charged. They're net neutral. So they're not going to move and conduct current, only the charged particles can. Finally, we have what we call non-electrolytes, and these are not conducting in solution at all. When they dissolve in water, they dissolve as pure molecules. So methanol, for example, doesn't dissociate in water. You just have methanol as a liquid, and then in water, it's dissolved methanol, but those methanol particles, still just methanol particles. So now there's no ions at all. Because there's no ions at all in this solution, that means that you cannot conduct an electrical current. So here's our kind of table to summarize what we were just talking about. Strong electrolytes are particles that dissociate completely and form ions in solution, and they conduct electricity strongly. Ionic compounds that dissolve all do this. There's strong bases such as sodium hydroxide, potassium hydroxide, and then we have strong acids like hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Now, weak electrolytes dissociate partially in solution. And what that means is you have mostly molecules and just a few ions. And because there's only a few ions, that means that the solution will conduct electricity very weakly. And any weak acid is the case there. And then finally, we have non-electrolytes in solution, which only form molecules and they do not conduct electricity. Any compounds that contain carbon, like alcohols, for example, methanol and ethanol, sugar is a good example of this, urea is a good example of this. Those are all examples of non-electrolytes in solution. Okay, so let's go ahead and take a look at this. Now I'm telling you these are strong electrolytes. So we have number 1, calcium chloride, and number 2, potassium phosphate. In water, when they dissolve, what do they form? Tell me what they form. So go ahead, fill out the response to the sample exercise. And then when you come back, we'll take a look at the answers. So go ahead, pause the video here. Okay, so now when calcium chloride dissolves, what it does is it forms the calcium ion is separated from the 2 chloride ions. So you get the calcium ion plus 2 chloride ions. Potassium phosphate does something similar, although this time we have a polyatomic ion. So we have 3 potassium ions and 1 phosphate ion. Okay, here we go. Which of the following reactions represent the dissociation of a strong electrolyte in water? So take a look through here. Do any of these look like they represent a dissociation of a strong electrolyte? And does it work with what you already know about electrolytes? Go ahead and pause the video. Well, let's look it through. First, we have a combination reaction. Well, that's not a dissociation, right? Dissociation could look like a decomposition. Also, we don't form an ionic compound here, NH4OH. It doesn't really look like a dissociation of a strong electrolyte in water, so we can't really choose that one. Methanol liquid goes to methanol aqueous. There's no ions in the product, so it doesn't look like a strong electrolyte to me. Sodium sulfate dissociates into 2 sodium ions and 1 sulfate ion. This is a strong electrolyte here. And then finally, ethanol down here looks the same as methanol. So the correct answer is C, sodium sulfate. Okay, next up, let's go ahead and write the equation for the formation of a solution of each of the following. Give me the dissociation reaction for potassium chromate, then the partial dissociation for a weak electrolyte, that is phosphoric acid, and then finally, when solid sugar dissolves in water, what does it form? And I just want to point out again, sugar is a non-electrolyte, so that should help you as you go through your notes. So go ahead and pause the video here, and when you come back, we'll take a look at the answers. Okay, so for A, we know that it's a strong electrolyte. What that is telling us is that all the ions in potassium chromate are going to dissociate from one another, and you know that you have 2 potassium ions and 1 chromate ion. So 2 potassium ion plus 1 chromate ion, they're all aqueous here, right, because they're dissolved in water. You're good to go. Next up, the partial dissociation of a weak electrolyte, phosphoric acid in water. Well, what happens here is, and I could accept this a couple different ways. If you removed all of the hydrogens, you get 3 hydrogen ions plus phosphate. Now, that's not the way it actually happens. So let's write it this way here in your notes. You have phosphoric acid, and it's going to sequentially lose each of its 3 protons. So the first time it loses a proton, it takes phosphoric acid, it loses a proton, and that leaves you with dihydrogen phosphate. Now, what's key is this is a partial dissociation. So that means that our arrow here, rather than just pointing from reactants to products, has to point both ways. And that's kind of the key part here that's going to tell us that we have a weak electrolyte. Okay, and then finally, we have solid sugar. Now, this is the easy part because it's non-electrolyte. All that happens is the solid turns into an aqueous, and that's all you have to do. So that's how you can show the dissolution of a non-electrolyte in water. Okay, so next up, we're going to talk about the word equivalence, because an equivalent is the amount of an electrolyte or ion that provides 1 mole of an electrical charge, either positive or negative. So in a solution, that means that the charge of positive ions is always going to be balanced by the charge of the negative ions, and therefore the concentrations of electrolytes in intravenous fluids are going to be expressed in milliequivalents per liter. So just so you know, this is what you're actually going to see when you do intravenous fluids. You'll get equivalents per liter or milliequivalents per liter. And 1 equivalent, again, remains 1 mole of electrical charge. So 1 equivalent is 1,000 milliequivalents. So if you had a solution that contained 25 milliequivalents per liter of sodium ion and 4 milliequivalents per liter of potassium, that means you have a total positive charge of 29 milliequivalents per liter. If you then have chloride as your only anion, in other words, you have a mixture of sodium chloride and potassium chloride, then you know that to balance out that 29 milliequivalents positive charge, you have to have 29 milliequivalents per liter negative charge as well. So yeah, just kind of want to point this out here because this is something that you'll run into in clinical IV solutions. Any of the positive ions, for example, if you have calcium and magnesium ions, those both carry a 2+ charge. So for 1 mole, it would have 2 equivalents. Just kind of keep that in mind as you kind of carry on in your career. And then you have like negative ions like chloride, acetate, dihydrogen phosphate. These are all examples that you may have. Lactate also shows up in IV solutions. And these each have -1 charge, so they're one equivalent in 1 mole. Carbonate, on the other hand, because it has a 2- charge, is 2 equivalents. And then finally, phosphate or citrate represents 3 equivalents. Okay, so here's how you go ahead and calculate equivalents. Now, this is not something I'm an expert at because I've been studying chemistry. I haven't been focusing on nursing, but this is something that's really important for your future. So I want to try to teach it to you now so you're kind of familiar with it. So let's say that the laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. So then the question is, how many moles of calcium ion are in 0.50 liters of blood? Well, if our milliequivalents are 8.8 milliequivalents per liter, and we have 0.50 liters of blood, we can convert from liters to milliequivalents using that conversion factor, 8.8 milliequivalents of calcium for every 1 liter of calcium. Next, we know that there's 1 equivalent of calcium for every 1,000 milliequivalents of calcium. So we're just converting from milliequivalents to equivalents, and that gives us 0.044 equivalents of calcium ion. Now, this is the tricky part that's kind of non-chemistry, that we wouldn't really think of things in chemistry terms. But remember, each equivalent is, you have 2 equivalents for every, you have 1 equivalent for every charge of an ion. So for calcium, which has a 2+ charge, that means there's 2 equivalents of calcium per 1 mole of calcium. So that's our next conversion factor, 1 mole of calcium ion for every 2 equivalents of calcium ion. That gives us 0.0022 moles of calcium ion. Okay, now if chloride is your only other ion that's present, what is its concentration in milliequivalents per liter? Well, remember, you don't have to do any molar equivalence here because equivalence is already in terms of charge. So 8.8 milliequivalents of liter of positive charge has to be balanced with 8.8 milliequivalents per liter of negative charge. Now, again, if you've done this before, tell me in the comments below. I'm really interested to hear how this has come up in clinic. I know a lot of you have worked in hospitals before. So let me know if you've come across this milliequivalents per liter concentration and how it's affected your work, because I'd be really interested to hear about that. Okay. Now, how about electrolytes in body fluids? So this is what we were talking about before at the beginning. So for blood plasma, for example, remember, plasma is the liquid component of your blood. So if you were to let if you were to take a sample of blood and let the blood sit, the plasma floats to the surface, floats to the top, while the blood cells and the other stuff all settle to the bottom. The blood plasma is like the aqueous component of the blood. And what do we know about electrolytes in blood? We know that it has to be charge balanced. So the total number of positive charges has to equal the total number of negative charges. That's, I mean, across the board, it's very difficult to isolate charge in one location or another. And of course, our body wouldn't do that. And it's going to vary due to nutritional, electrolyte, and fluid needs of a given patient. So that's going to be the case for electrolytes in body fluids. Okay, so here's for IV solutions. So we want to talk about the solubility of the different ionic compounds so that we understand how things can be put in an IV solution. Remember, an IV solution has to be fully soluble. Like there can't be any ionic compound that would precipitate out, or you would get a solid when you entered it into your bloodstream, and that solid would disrupt the flow of blood and probably kill the patient, I assume. So we know that an ionic compound will be soluble in water if it contains one of the following. If the positive ions are lithium, sodium, potassium, rubidium, cesium, or ammonium, or if the negative ions are nitrate or acetate, if they're chloride, bromide, or iodide, except when combined with silver, lead 2, or mercury 1 cations, or sulfate when it's combined. So sulfate ions are soluble except when combined with barium, lead 2, calcium, strontium, or mercury 1. So if ionic compounds don't contain at least one of these, the ions are insoluble. So these are going to be our solubility rules, and this is what's going to apply to the next chapter. Now, what I'm going to give you is, on the test, I'm going to give you this exact table, but you need to be able to read the table because I'm not going to spend the time to explain it to you on the test itself. Okay. Sample exercise number 5. So this is going to be based on equivalence that we were talking about before. So go ahead, pause the video here. Try to understand the equivalence talk that we were talking about before. And then when you come back, we will go over the answers. So go ahead, pause. And we're back. So in 1 mole of iron 3, there are how many equivalents? Well, there's 3 positive charges on iron. So that's going to be 3 equivalents. In 2.5 moles of sulfate, there are how many equivalents? Well, 2.5 moles of sulfate, you know, it's a 2 negative charge. So that's 2 equivalents per 1 mole. So a total of 5.0 equivalents. Then finally, an IV bottle contains sodium chloride. If the sodium is 34 milliequivalents per liter, then the chloride has to be, well, it has to be the same. We know that the positive charge has to balance the negative charge. So if we have 34 milliequivalents of a positive charge, we have to have 34 milliequivalents of a negative charge. Okay, so let's go ahead and look at solubility next. So gout is an example of a condition that can occur if uric acid builds up in blood plasma to exceed its solubility of 7 milligrams per 100 milliliters. So if uric acid builds up in the bloodstream, it basically forms a solid. And again, that leads to very dangerous conditions, including gout. Okay, so now what we want to talk about is we want to talk about solubility. And solubility is defined as the maximum amount of solute that dissolves in a specific amount of solvent. And keep in mind, this is always given for a certain temperature because it will depend on the temperature. And the way that we express it usually is grams of solute per 100 grams of solvent. And for the most part, we'll talk in terms of water, especially in this class. We basically are just going to exclusively deal with water as our solvent. Okay, now there's 3 different ways that we can describe a solution. A solution can be unsaturated. Unsaturated means that it doesn't contain the maximum amount of solute. In other words, more solute could be dissolved in that solution if you did. Now, of course, eventually you dissolve the maximum amount of solute, and at that point, we call this a saturated solution. So what happens now is you have the maximum amount of solute that could possibly dissolve in that amount of solvent. And so you end up with undissolved solute at the bottom of a container. And however much of that is dissolving is then equaled by the amount of solute that's recrystallizing. So you have a net same amount of solute dissolved. This is what we call saturated. In other words, it's the maximum amount of solute dissolved in it. Oh, and then maybe we don't talk about it. I guess we don't worry about it. There's another condition called supersaturation. We'll talk about that later. Okay, so now let's try to figure out if each of these are saturated or unsaturated. A, salt disappears when put in water. Is that from a saturated or an unsaturated solution? And then finally, sugar added to a cup of water does not disappear, but sits at the bottom of a cup. Is that describing a saturated or unsaturated condition? Well, salt disappeared when put in water. That means it dissolved. So that solution must have been unsaturated. On the other hand, when sugar was added to the cup and it did not disappear, it sat at the bottom of the cup, that indicates that the solution was saturated. In other words, the full amount of sugar was dissolved, and so you weren't able to dissolve any more sugar. Okay. Here we go. At 40 degrees Celsius, the solubility of KBr is 80 grams per 100 grams of water. Identify the following solutions as either saturated or unsaturated and explain. So I'll do the first one with you, and then hopefully that'll help you understand B and C. So let's look at A together. A says if you have 60 grams of KBr added to 100 grams of water at 40 degrees Celsius. Well, the solubility is 80 grams of KBr per 100 grams of water. So we have 60 grams of KBr per 100 grams of water. That's clearly less, right? So that's going to be an unsaturated solution. Now try to do the same, but keep in mind that the amount of solvent is going to change. So 200 grams of KBr per 200 grams of water, how does that relate to our solubility up here? So pause the video, and when you come back, we'll take a look at the answers. Okay, so I hope that made sense. If you have 200 grams of KBr per 200 grams of water, that's clearly the same as 100 grams of KBr per 100 grams of water. And that case would be saturated because it's over the solubility limit. Then finally, 25 grams of KBr to 50 grams of water, well, that'd be 50 grams of KBr to 100 grams of water. That's clearly less than our solubility, so that's another unsaturated solution. Okay, so how does temperature affect solubility? Well, it depends on what type of compound that you're talking about. For solids, usually solubility will increase as temperature increases, but for gases, the opposite is true. Gas solubility decreases as temperature increases. So how do I want to say this? Like, what do I want to say? So for example, potassium nitrate at 20 degrees Celsius, you can only dissolve about 30 grams of potassium nitrate for every 100 grams of water. But if you bump the temperature up to 80 degrees Celsius, all of a sudden now you can dissolve a full 165 grams of potassium nitrate for every 100 grams of water. That's pretty impressive. On the other hand, gases, as they heat up, as the solutions heat up, the gases will bubble out of solution. That's why next time when you have to boil pasta, for example, or anytime you're boiling water, if you're steaming or whatever on the surface, just take a look at the pot before it starts boiling. You'll start seeing bubbles at the bottom of the pot. Now, those bubbles don't represent the water boiling. It's at too low of a temperature to boil. What they do represent is they represent the gases that are dissolved in the water coming out of solution. And that's because, again, as the solution increases in temperature, the solubility of those gas particles decreases. Okay, here we go. So that's all we have for that. That's it's a really quick discussion, but we have a lot of material to cover in this chapter. So, or in this class, I should say. Why could a bottle of carbonated drink possibly burst or explode when it's left out in the hot sun? And then finally, why do fish die in water that is too warm? Think about what I was just telling you about the solubility of gases in particular, and pause the video here, try to come up with your answer, and then we'll look at the answer on the next slide. Okay, so remember, the key thing to remember here is that the solubility of gases decreases as the temperature increases. So for the case of our carbonated drink, well, we have a bunch of gas that's dissolved in liquid. We're increasing the temperature of that liquid. The gas can't fit in there anymore, so it's going to try to burst out of it. But the can or the bottle contains just a very little amount of space. So it'll get to the point where it's pressured enough that it can actually burst the bottle. And then finally, fish die in water that's too warm, because as water is warm, water warms up, oxygen is less and less soluble in it. So, and of course, fish, just like us, need a certain amount of oxygen to be able to breathe. So if the concentration of O2 is too low, it's just like us, if we're running out of oxygen in like I don't know what kind of situation we'd be in space or something like that, or in a submarine or something like that. So because oxygen got less soluble, all of a sudden those fish can't survive. Okay, all right. Now we're going to look at, sorry, I guess I forgot we had a whole discussion on solubility pressure here, which brings us to Henry's law. Henry's law is just a sort of a brief extension of our gas laws that tells us that the solubility of gas in a liquid is directly related to the pressure of that gas that's above the liquid. And the higher the pressure, the more gas particles will dissolve in the liquid. And that's all you need to know. Basically, the higher the pressure is, the more particles will dissolve. That's why you have your soda cans and soda bottles under pressure. When you open them, you hear that. That tells you that you reduce the pressure. That's because under high pressure, you get more CO2 molecules into the soda or the water. And of course, that's what gives you the pleasant fizziness when you actually drink that soda. Okay, now I already showed you the solubility rules earlier, basically telling you that an ionic compound will be soluble if it has one of these positive ions, or one of these negative ions, or chloride, bromide, iodide, except when it's silver, lead 2, mercury 1, or sulfate is soluble usually, except when it's combined with barium, lead 2, calcium, strontium, or mercury 1. Ionic compounds that don't contain those are insoluble usually. So this brings us basically, when you mix certain aqueous solutions, you get certain insoluble ionic products. And this is useful because you can actually do barium dosing in your I think your intestines here, that's an insoluble ionic compound. And it's a way that you can actually see X-rays a little bit better. So that's an example of an insoluble ionic compound coming in handy in a medical location. Okay, so here, how do you use your solubility? Well, let's say that I ask you, okay, is this compound soluble, potassium sulfide? And the answer is, well, let's look at our table. It contains the potassium ion and the sulfide ion. Now, sulfide's not down here, but potassium is here. And that means if it's in the positive ion chart, that means that it is soluble because it contains potassium. Calcium nitrate, also soluble because it contains nitrate. How about lead 2 chloride? Well, let's go back here. We know that chlorides are usually soluble, except when combined with lead 2. That means lead 2 chloride is insoluble in water. Sodium hydroxide contains sodium, so it's soluble. And then aluminum phosphate, neither of those are on our chart. So there's no soluble ions, so it's insoluble. Okay, so now think about it this way. Look at these. So we have cadmium sulfide, lead, iron 2 sulfide, lead 2 iodide, and nickel 2 hydroxide. Why are each of them insoluble in water? Tell me what's up. And let's take a look. Well, cadmium sulfide contains no soluble ions, so we wouldn't be worried about that one being soluble at all. Iron 2 sulfide, same deal. We wouldn't expect either of those ions to be soluble in water. Lead 2 iodide, well, iodides are soluble except when combined with lead 2. So lead 2 iodide also insoluble. And then finally, nickel 2 hydroxide, neither of those ions are expected to be soluble. So that's insoluble as well. Okay, that brings an end to our discussion on solubility. We have one more lecture left in this chapter. So make sure start the homework now, and I will see you soon to wrap up this chapter on solutions. Until then, bye-bye.